Hello everyone again. I hope you can hear me and can see the screen. I'm going to just briefly for the next 29 minutes or so go and talk about upfront simulation. It's also referred to as virtual prototyping, digital simulation. And to break up the presentation for my session, I'm going to introduce some sort of polls just to sort of get an idea from the audience of how much you are using simulation or how much you're aware of it. So we're going to start off with the first poll. And my colleague Emma is going to help me with this. So basically, we just want to get an idea of if you're doing any simulation or not. Even though you might be doing all the options in there, just use the most appropriate selection. Okay, let me see what I can see. Let's make the screen a bit bigger. Ah, that's perfect. It looks like everybody is using experience, which is very, very common when I go and see customers, which then leads me to the next slide. So the question is, why do we need to do simulation? Typical scenarios would be that we should be able to validate designs earlier. I guess, yes, you can use the experience as well. And the other big option is obviously you don't want any failures happening within the industry, so simulation can actually help you validate that. And this one here, you have the option, I guess, when you're basing it on experience, everybody's under pressure with time. So obviously, you don't have the ability to check different scenarios. So materials is one. And then most importantly, in my opinion, is to design with confidence, because this gives you the ability to check whether a design will fail, because you actually can test it. What happens if it's dropped? And many more what if scenarios. So it gives you the ability to try these under the time and pressure you guys are under, rather than just basically just based on experience, which will happen anyway. And it can help you to basically reduce design and development times when you're under a lot of time and pressure. And I guess avoid in field failures. You don't want to be sitting in a plane and seeing that off the wing of the plane. And obviously with the what if scenarios, you have the ability to check different scenarios and basically innovate. And again, in my opinion, the most important one will be to be able to design more confidently. Okay, so for the next poll, I just want to get an idea. If you are, obviously, I think that is probably self-explanatory, because everybody sort of views said they weren't using any software. So I think this would probably be a straightforward one. I'm guessing the last option. Okay, this is a little bit a mixed bag. So we have people using Inventor, other technologies, and also what I suspected. So basically we've got a nice split between the audiences. So if I go back to my screen now, Emma. Thank you. So as from Symetri, we have traditionally been supporting our clients like yourselves around the Autodesk portfolio. But going back just before the pandemic, we basically started looking into a partner, Altair, to provide some sort of complementary solutions to work alongside the Autodesk portfolio. So let's go through these just to give you an idea what options you may have. Obviously, this is very popular. A lot of customers will be aware of Inventor Stress. This gives the customers the abilities to do a linear analysis, which is probably the most common type of analysis required by many customers. And that gives you the ability to analyze single components and also assemblies, as you can see here. And then for technical jargon, as I will use, it allows you to have different types of elements. So this is what you can do currently. So anybody who has Inventor or product design and manufacturing collections has access to this, and you can start using it. This is probably not commonly used. It is available only under the assembly environment. It's called frame analysis, and this is dedicated for structural framework type analysis. If you're familiar with a frame generator or content center and you create content using that library, then you have the ability to be able to do a structure analysis or beam analysis, different terminologies, to do the same thing you do in Inventor Stress using linear and model. And as you can see here, it only does beams. You can look at shear force, bending moment diagrams, and it's pretty powerful. But obviously, it's only available if you are using a frame generator or content center libraries from inside Inventor. And then this is probably not also very common, because you will not see that in your default Inventor installation, because it's not there. It's in the same area as your Inventor Stress analysis, but you can only see it if you download this from your download section from your account. And Inventor Nastran is a very powerful comprehensive solution, and it does a lot more than Inventor Stress. It does a buckling, fatigue, non-linear analysis. You can have different types of element types in there using solid shells and beams. You can do pretty complex analysis in here. And then the fusion simulation software, like Inventor Nastran, again, is very powerful. And it has similar technologies. It's the same solver as Inventor Nastran, but it has a different look and feel. The interface is very sort of new, and it has some specialist analyses which are not available inside Inventor Nastran, and that's primarily things like electronic coolings. It's a bit like it's a bit like fluid flow analysis. Then you have the powerful shape optimization, which is similar to generative design, but in a different way. And then you have the injection molding simulation, and this is the area which is being continually expanded using the Flex Sim, which you saw earlier, and also the Cadence. So this is getting more and more developed. So it is a pretty powerful technology. And if I was to compare between Inventor Nastran and Fusion in terms of ease of use, this technology is a lot easier to use than Nastran. Okay, time for the next poll. Okay, just curious to see what sort of response we get. Okay, so we can see here the most time-consuming process is model preparations, and the setup and run times can be basically less time-consuming, but then again, model preparation also includes model simplification. So whether simplification or preparations, I guess that seems to be the most time-consuming process. And thanks for that, Emma. Okay, so the technologies I mentioned, I would refer to them as traditional FEA solutions, and that also extends to softwares like ANSYS, Abacus, COMSOL, Nastran. All are referred to as traditional solutions, and they all have one thing in common. They all require a mesh, this triangulation of elements in the software for it to give us any form of results. And then the size of the mesh will have a huge impact on the solution times. So basically, the smaller the mesh size, in your models will have a huge impact and will take a lot longer to run, but the results will be more accurate. So if the element sizes are smaller, the results may not be that accurate. So there has to be some sort of compromise, which you guys will probably juggle between. And then the most important one, the reason we go through model preparations or simplification is that we need to enable the mesh process, because the geometry, the golden rule is make it simple, which is the other extreme when designers are trying to add every single detail in geometry. As an FEA person or an analyst, we are going to the other extreme. And then again, depending on the detail, the complexity of the models and the size of the models, this can be very, very time consuming, as you saw in the poll. And here I have some examples which are the problem areas where mesh will fail. So things like assemblies with big and small or thick, thin parts with gaps, small geometry features, and then an example here of an extreme geometric complexity. You will not be able to analyze that in a traditional FEA solution. And then we have geometries. This is very common in castings type examples where you have a lot of transitions or splinter faces. So these are what we refer to as problem areas which need to be simplified for the mesh to be able to be created. Now, we came across a technology several years back referred to as Autodesk SimSolid. When I first saw this software, it was absolute pure magic because the software actually works on the CAD geometry without any simplification. Because it does not require a mesh. So if it doesn't require a mesh, there's no need for us to simplify it. And the other thing I like about it is absolutely fast to run. So if you have models which you spend several hours trying to sort of clean the model or do the geometry simplifications or preparations, there's no need to do that. The reason being is that the software is very, very powerful, and it ignores and sort of works around all the small features, things like what we refer to. So these are not an issue. And what I'm going to do here, basically, well, before I do that, because we have clients like yourselves using Nastrans, we do not expect you to sort of change the way you're doing things. So we focus the use of Autodesk SimSolid in these 4 different areas. The first one is complex models. Now, softwares like Nastran or Inventor Stress will not be able to be analyzed with this sort of complexity where it's a 3D printed part or it's lattice structures or organic structures, something, for example, which is pretty detailed and complex. So this is an area where Autodesk SimSolid can be very, very powerful. The other one, which is probably the most popular option within our clients, is when you have super large scale models. This can take a long, long time to set up and prepare. Whereas if you already got the model, you can take it into SimSolid and it basically will just work as it is from the model. Very little setup required. And then again, original models, if you are into both the connection, for examples, as you may well be aware, if you use Inventor Stress or Nastran, you cannot use both the connections. You have to suppress them, then you got to recreate them again inside, let's say, Nastran or Inventor. Well, you can't do them in Inventor Stress. So this is a great example as well. And finally, as you will see in a moment when I do a live presentation on an example, the results are absolutely super fast. Okay, but before we do that, just want to sort of get an idea of how long you normally spend. I'm hoping we have some saying more than an hour. Let's see. Okay. Is everybody still there, I guess? Okay, let me go straight into the presentation. Oopsie daisies. Let's have a look now. Okay, so what you see on the screen is the Altair SimSolid interface. Is basically, as you see, notice it is separate from Inventor Stress and outside Inventor. And even though it is separate from Inventor, you still can open Inventor files along with other different kind of file formats, CATIA, SolidWorks, Unigraphics. But I'm going to open here a PySolid file format. So what it's doing here basically is going through and importing the actual geometry into my SimSolid software. And the first thing you'll see on the dialog box is that you will see very similar to also Inventor Stress, that you need to define the contacts between the geometries. Now I'm gonna, if everything's touching, the gap and the penetration options can be set as 1. So it'll keep the default settings. And then it goes through a process of creating hundreds and hundreds of contacts. Then it's got this warning saying that there are some components in here which are not connected. So I'm going to go in here. Well, everything seems to be connected here, so let's zoom out. And then if I look at group 1, I can put the little magnifying glass on. You can see these are little sort of connectors. I mean, I could go and increase my gap between the components and have them, but as an FEA person, I don't think these will make any difference to my results, so it's pretty easy to suppress them. So you don't need to suppress these also inside Inventor, you just leave them as they are, bring the whole thing in, and you can suppress them from here. So once they have been suppressed, then I think everything should be connected. You can check this from this little button here. Everything seems to be connected. So there is your sort of, now the only thing I need to do here, because it was a step file or a PySolid file, you need to apply some materials. So I'm going to apply everything as steel just to keep it simple. So now we have defined the materials, and the next step is I want to find out, as an example, I want to see how apply the weight of some maintenance workers with their kit on here and see how strong it is. But one thing I want to show you here, which I think is absolutely powerful on SimSolid, is if I click on that bolt there and right hand click on here, the software creates a special contact between both the connections. You can see there, you can barely see it. I see sort of yellow cursors, and that basically is a sliding contact. So it creates a sliding contact between the bolt shank and the hole plates, and the bolt and the nuts are fixed. So it does that automatically. So saving you a lot of work and effort. And now what we're going to do here is we can go and create a structural linear analysis. And the only thing I need to do here are two things. I'm going to restrain down here. So I'm going to fix that one. Inside Inventor Stress and Nastran, you would have to create 6 separate faces if you want to check the reactions on each face individually. Inside SimSolid, you can do it all as one or separately. It's entirely up to you. So that's done that one. Now, typically, this type of example, you will not be able to run inside Nastran or maybe Inventor Stress because it has to mesh. You may remove this platform, for example. That's one way you would do it. You might remove the handrails because you want to make it simple. You want to be able to mesh it. Here, it doesn't really care where you do it. So I'm simply going to apply a load on the top here. Let's put that here. It pushes it on. You see there? It's going to go all the way across, and it's going to be in the Z direction. Let's say minus 2,000 newtons, 200 kilograms. And that's it. So you probably will be spending time on this in the traditional tools by suppressing all the handrails, removing all the bolts and keeping it simple. And then in a typical process, you have to run it 3 or 4 times to get the mesh convergence. Now, if I press run here, hopefully I've done everything correctly, you'll see in the bottom left-hand corner, the software is going through 3 iterations automatically by default. And I'm using a laptop here, so nothing powerful. And within less than a minute, I guess, we'll have some sort of results. This is how fast the technology is. Okay, yes, that's done. So we'll go and have a look at some results just to give you an idea to see what the behavior is. So that looks okay. And if I just show it deformed, not that one, you can see it's deformed and you can do the animation. So it gives you the behavior as we would expect. And the other thing I like about in here, which is very powerful, is if you want to look at the bolts. If I go into, not this one, it's down here, there. It creates a table of all your bolts in the model with all the forces, shear forces, and bending moment, and you can export that to a spreadsheet and then start interrogating. So I think that's pretty powerful. So I just want to give you a brief sort of overview of what the technology can do. So I hope that was pretty impressive in the time scale. I've demonstrated that in traditional tools. I don't think you'll still be doing your model preparations. So let's go back to the slide now. Okay, just as the final part of my presentation, as I was fortunate to be in Sin City, this is a snapshot of my class presentation. I won't have obviously time to go through all of it. I'm just going to give you a look and feel of what the class was about. In the handout section, you have a PDF of the presentation, and you also have a PDF of the handout as well, which you can access. And I basically went through 4 different sections, giving you some sort of linear analysis, impact analysis, and different sort of areas and further learnings. But I just want to give you a feel of what it's all about. Basically, it's broken down in some sort of tips and workflows. And then I did a live demonstration of one of these examples, which I won't be doing today, obviously, because of time. So I just want to go through to see what it's all about. So the first section is the linear analysis. And it was basically, this was a question which I get asked a lot from the offshore industry, primarily when they do lifting type of scenarios. And this was going through that same example. So basically, some of the tips are suggested here that if you have a fabrication or you have an assembly which is all welded together, trying to reduce the number of contacts in event of stress or Nastran, you might as well combine the parts together. It makes no difference. You have less contacts, so it'll be quicker to run. And then this is also very common. I see time and time again when I see our customers using solid elements on long, thin, slender objects. So as a rule of thumb, if you have a component with a ratio of 1 to 50, thickness to length ratio, then I suggest you use the shell elements option just so that it runs faster and then you get more accurate results. The third tip looks very simple. I want to take a shaft, a step shaft, and I want to create a simply supported connection. Now, obviously, solid elements don't have pin type connections, so it's pretty impossible to do this inside event of stress. So you can use rigid body connection, which is a very special type of connections, so that you can get, like I call it, referred to smiley face type of result. And this sort of then correlates our hand calculations within 1%. So use rigid bodies to be able to do pin type connections at the end of a solid shaft. And then when you are using shell elements, then I suggest that you use offset bonded contacts rather than using bonded contacts, because bonded contacts only restricts 3 degrees of freedom and offset bonded has 6 degrees of freedom, just to give you the difference between the 2 types of contacts. And then the last one, option 5, basically is that when you have a scenario when you want to be able to, when you have rigid body, and I don't know if you use Nastran or anybody, or when you start using it, you'll have an E5000 error, which basically means that it's not fully constrained. But then again, you decide, well, it's already fully constrained. Use rigid springs or grounded springs to stabilize your models. And then the last one here, I was demonstrating that you can use rod elements to demonstrate the slings of how you sort of lift the actual spreader beam. So this gives you an idea of, so I go through this type of tips and tricks, then I go through a live demonstration. When I was in Vegas in my class, obviously in this case here, you can look through my handouts, going through the workflows. But at least it gives you an idea of what the class was about. Hopefully within a week or two, I guess, it will be available also on the Autodesk University website for you guys to have a look at.